Hi, my name is Hadir Istiak and this is my physics video for my roller coaster. In this video, I'll be explaining how I made my roller coaster, what materials I used, and how I kept it all stable. Also, later in the video, I'll be explaining the energy transfers and how they relate to our physics unit and the concepts we've learned in class. This is going to be through the appendix document that you get, as well as the diagram that I'll be putting inside the video. Thank you. Hope you enjoy. Stability is an important part to this project because it dictates how your roller coaster will perform when the marble is finally released from the start gate. Without correct stability, you can experience a lot of energy loss, and I didn't want that in my roller coaster since I needed the marble to go the full way. The first way I ensured stability was to use wood as my base, as everything that I was going to glue and attach onto it would be stable and on a level surface. Next, I needed to create a stand for which I can attach my track onto. I glued together 4 pieces of wood, 60 by 10 by 5 centimeters, which I created a solid rectangular prism with. I glued this onto the start of my track, which then allowed me to staple in the beginning of the track onto the top. This made the first section of my track relatively stable, as there was no shaking when I let the marble leave the start gate. The first time I experienced shaking was with the loop. When the marble went through the loop, the track was shaking, which meant the kinetic energy was being lost. With a lower kinetic energy, the marble was having trouble reaching the first hill. To make the loop more stable, I hot glued 4 wooden dowels, 2 on each side, beside the hill. The force of the dowels from both sides allowed for the hill to stop shaking, which meant that the kinetic energy was increased. I came across the same problem with the 2 other hills I created. When I was testing it the first time, the marble would have too much speed and bounce off the track. If I put the marble too low, it wouldn't make the first hill. I used the same dowel method and it proved to be useful as they straightened out my track. I also needed the places where the track could rest on an object or stick to the ground as to provide a stable track for my marble to navigate through. For the loop, I glued 2 cut-in-half plastic cups on the board and taped the track to the cup. This allowed for the track to stay stable as well as provide enough of an angle downwards at the end so that the marble had a chance to go over the first hill. I tried using the cups method for the 2 of my hills, but that proved ineffective. I decided to use Velcro instead. I glued the rough side on the board and glued the soft side to the track. When attached together, it was very stable and had a strong adhesion to it. The materials that I used for this assignment proved to be very useful, and mostly all materials that were in my list were used. The first item that I used to construct the coaster would be wood. I wanted to use wood as it was a very stable material and it was easy to attach things to it like the tracks, the cups, etc. Next, I used pipe insulation for the track. Pipe insulation was great as it had the perfect curvature for the marble to roll onto as well as the malleability. I could twist and contort the track as much as I wanted to make my hills and the loop. I used plastic cups for the support of the track. 2 were glued onto the board so the track could lay on it and be stable. I taped the track to the cups so that the track wouldn't be in free form and that it could have a structure to it. I ran out of pipe insulation by the beginning of my first hill, which meant that I needed to connect more track. I bought steel wire, which I cut into a sizable 5 centimeters. I fed half of this through the insulation on the board and the other end to the new piece of insulation. The wire worked as a connector, which then I taped over. This also allowed for a bit of flexibility as the connecting point was the beginning of the first hill. Velcro was used to fasten the track onto the wooden base. This worked well as the Velcro held the track securely in place and provided minimal anomalies. Another great thing about Velcro was that I could manipulate the track wherever I wanted. For example, when I was first testing it, the second hill was higher than the first, so the marble couldn't reach the top of the hill. I adjusted the Velcro and then the hill became lower. The dowels were used to stabilize both the hills and the loop to account for energy loss that I was previously experiencing without the dowels. If I had the opportunity to do this assignment again, the first thing that I would change about my roller coaster is actually having an inclined launch. By looking at my coaster, the end of it was horizontal, meaning that the marble had a horizontal launch. This means that I didn't fulfill one of the requirements of the assignment, so I lost marks in that specific area. The horizontal launch worked to my favor as the marble landed consistently 3 times in the level 4 zone. Also, in my appendix, you can see that the working out for my launch velocity was very simple, as I only had to work in one direction. My friends had to work in 2 directions because they had an inclined launch and had to consider an angle. My angle was 0, so I didn't have to consider that. Other than the inclined launch, I don't think I would change much as the coaster turned out to be a success. When looking at other people's coasters, they definitely had design elements that mine were lacking, such as engineering or even decorations. I decided to go for a simple design and something that wasn't at all innovative. If I did this again, I would definitely make my roller coaster more appealing to the eye, as well as improve my engineering skills by innovating and trying new things in my design. So this part of the video will talk about the energy transfers that occur throughout my roller coaster. Starting off, we have the start gate, right? So the start gate has a 46 centimeter height, so this means that it has a potential energy. The EG is 0.22563 joules, and that gets converted into kinetic energy because of the conservation of energy. And all the working out and everything will be in the appendix document that you get with this video. So if you need to refer to anything, I've included all headings and titles, so don't worry about that. This all gets converted into kinetic energy, and with kinetic energy, of course, there's velocity. So the velocity that I got, I calculated, was 3 meters per second. So as it goes down, it's traveling with a velocity of 3 meters per second, and the EK, or the kinetic energy, at the bottom point of the incline of the start gate would be 0.0225 joules. So not a very big difference. Now, as we go through the first loop, the minimum velocity needed to actually do the whole loop would be 0.204 meters per second. And what this means is, as the marble goes across the hill, it's the minimum velocity needed to just go over and complete the whole loop. So obviously this is a very small velocity, and that's what it needs to complete this. So afterwards, after the marble exits the loop, it has a velocity of 1.78 meters per second, and the kinetic energy is 0.007921 joules. Now, obviously this is a higher velocity because it's gaining. You actually start with kinetic, and then you have potential while you're going, and then it all gets converted back into kinetic energy, which means that you have a higher velocity at this point because you're converting so much. Now, and then after the loop, it actually goes to my first hill. So the first hill has an EG, or gravitational potential, of a 0.0073 joules. So as it crosses my first hill, it's already traveling with the velocity beforehand from after it completed the loop. So it's already traveling with that 1.78 meters per second. So after it completes my first loop, the velocity at the bottom of my after it completes the first hill, the velocity at the bottom of my first hill would be 2.47 meters per second. It's a jump, or it's an increase from the velocity that I experienced after my loop, because there's not that much friction happening, and obviously going through a hill or going over a hill is much more different than going through a loop. The EG for the second hill would be 0.068 joules. This is obviously lower than the potential energy for my first hill because the second hill's height is actually 14 centimeters, whereas the first hill's height was 15 centimeters. Now, the velocity as it completes my second hill would be 2.50 meters per second. So you get a bit of an increase, which is interesting to me because the height was actually lower. So maybe there was lower friction at that point, or the marble went more smoothly over the second hill and everything like that. So, and then the kinetic energy at the bottom of my hill would be 0.0157 joules. Now, as the marble exits to my horizontal launch, sorry about that, I forgot there was that you had to have an inclined launch, so I'm sorry about the horizontal launch. But as it approaches my horizontal launch, the actual launch velocity is 0.51 meters per second, which is interesting because it slowed down my marble so much. And the reason because of this, in the video, the marble actually lands very hard on the bottom of the second hill, so it creates a lot of shaking, which obviously you lose kinetic energy doing that. And obviously, when it exits with a lower velocity. This is why. And the E loss actually it was interesting because I had to do the theoretical versus the actual. So in my document, I just need to pull it up. Sorry about that. The E loss, the energy loss over the whole two tracks is 0.022 joules, and the energy, the kinetic energy at first is actually 0.0225 joules from the theoretical or the expected, right? And the actual kinetic energy is 6 times 10 to the negative 4 joules, which is very low. And this is obviously because of the energy loss that I experienced with the shudder and the shaking at the end of my roller coaster. This has been the descriptions of the energy loss. I hope it was interesting and intuitive. Just to end things off, I wanted to talk about the strategies I used to minimize energy loss. So again, to reduce energy loss, I tried to keep the roller coaster as stable as possible. This meant attaching wooden dowels to each side of the two hills as well as a loop. So the specific energy loss that I was experiencing was kinetic energy loss. Kinetic energy is the energy that an object has while moving. So the object in this case would be the marble. The lower the kinetic energy, the slower the ball will move because of the velocity variable in the equation, half mv squared. You obviously can't change the m as it will stay as a constant. And I tried my best to reduce energy loss, specifically kinetic, but as you can see, the shudder or the shaking at the end of the first hill really slowed down my marble, and it just went over my second hill, like thankfully, which I'm great for. But if I could make that more stable and actually attach one more wooden dowel to the other side, because in the actual video and other pictures there's only one dowel attached to the right side of the coaster. So if I could add just one more dowel and make it more streamlined or more like bunched in together, it would make it go so much smoother, and the shuddering or the shaking would stop, and I wouldn't have as much energy loss or E loss as I had previously with the shaking.